Hi everyone. Do you ever wonder if the equations that your physics teacher gives you are real, or if they just made them up by throwing a bunch of letters together? Well, in today's lab, you're going to have the opportunity to figure out whether or not F equals ma is an equation that really truly describes how objects behave in our universe. Here's the setup for this lab. You're going to have a cart that has some amount of mass to it. You're going to apply a force to that cart by pulling on a string. And when you pull with that force onto the mass, it should accelerate, meaning it will speed up. This is called the F equals ma cart lab, where a force is applied to a mass, and so it accelerates according to F equals ma. This is the equation in question for today's lab. This is Newton's second law of motion, which says that the net force being applied to a mass will cause that mass to accelerate a certain amount. You could also rearrange this equation to figure out how much an object will accelerate or speed up. And you could solve for acceleration by dividing both sides of the equation by m, in which case you would get force divided by mass equals acceleration. Now, is F equals ma a valid equation? Does it accurately describe how matter and objects behave in the real world? If not, then you probably don't need to learn it, and you'll be able to prove once and for all that your teacher's just making stuff up. So let's figure out if that's true or not. Here's the first question we're going to try to answer in today's lab. If we take an object that has a constant mass, like this cart, which is not growing any larger or smaller, and if we change the amount of force being applied to it, say by pulling on the string harder or pulling on it softer, then how will that affect its amount of acceleration? Now you can probably guess that pulling harder on the cart is going to make it accelerate more, but is that really what's going to happen exactly? We'll figure that out today. And the second of our two questions in today's lab is, if instead we put a constant force onto an object by pulling on it the same amount every single time, but we change its mass by making it larger or smaller, maybe by adding weights on top of it or taking mass off, then how will that kind of change affect the acceleration of the cart? So how can we hope to answer such complex questions? Well, it's simple. We're going to use science practices. What's the first thing a scientist usually does? They collect data. And then what do they do with that data? They usually visually display it in the form of a graph. Then using that graph, they can draw a conclusion of some kind to answer whatever question they had. So we're going to go through that process, and we'll see if F equals ma is an equation that matches reality and how things actually move in the real world. Here's how we're going to get started. The first question was asking about if we change force while the mass stays constant, how will that affect acceleration? Let's look at F equals ma again. In this equation, if mass is held constant, so here's the m, and we're saying that's going to be held constant, if we change the amount of force being applied to a cart by, let's say, using only half the amount of force that we did originally, maybe instead of pulling really hard, you pull kind of gently, how would that affect the acceleration of the cart? Well, you could probably figure out that if you apply less force, you're going to get less acceleration. The cart won't speed up quite as quickly. So you could say that for half of the force, you'll only get half of the acceleration. And that makes sense because if the number that you plug in for the mass of the cart is always staying the same number, the same value, and the answer of m times a is decreasing by a factor of 2, then it must also be true that a is decreasing by a factor of 2. If you have half of a, then you're going to get half of f because m is staying constant. So if you, instead of thinking about using less force, instead think about using more force, let's say you double the strength with which you're pulling on that cart, and you use twice the force, how would that affect the acceleration? Well, you're going to end up getting twice as much acceleration. So whatever happens to F seems to also be happening to A in exactly the same way. This is called a proportional relationship, where F and A are changing together in exactly the same way. If one of them doubles, the other doubles. If one of them triples, the other would triple as well. So here's what this would look like in your lab. If you collect a bunch of data about different amounts of pulling forces and you plot that against the acceleration of the cart when all those different pulls happened, you should get a bunch of data that looks like this. And from the shape of this data here, I can figure out that more pulling force resulted in faster accelerations. So if I took a best fit shape and applied it to this data, then it might look like a proportional shape. And there are all kinds of shapes that you can fit to your graphs. There's linear, proportional, inverse, and proportional is one where there's a straight line fit and the line starts exactly at the origin, at 0, 0. Now, that makes sense because if you don't pull on the cart at all, if you use zero force, then the cart should not accelerate at all. So there should be zero acceleration. So 0, 0 is always an important location for a proportional relationship. So in today's lab, F equals ma will be confirmed as a real valid equation if your data for F and A shows proportionality, meaning you get a proportional relationship on your graph. And F equals ma will be debunked, meaning it's not a valid relationship if you don't see a proportional relationship between A and F. So that's going to be how you figure out if F equals ma is a real equation or not based on question 1. But remember, there's a second question as well. Question 2 says, if instead we put a constant force onto an object, so okay, let's take Newton's second law of motion and let's make F constant in this case, and we change the mass, then how will that affect the amount of acceleration? Okay, so let's take the mass in this formula and let's just double it. Let's say we are pulling on a cart and then suddenly it weighs twice as much. It has twice as much matter in it. Well, how would that affect the rate at which it speeds up? Well, if you get something to be heavier, it's going to be harder to move. So in this case, the acceleration would decrease by a factor of 2 instead of increasing by a factor of 2. So double the mass should result in half the acceleration. Now this kind of makes sense because m and a, just like in our last example, have to get multiplied together to equal f. So if the f answer is supposed to stay the same value, but one of the things going into that calculation doubles in value, then the other thing is going to have to half in value, so that when they get multiplied together, we still get the same answer at the end. So double the mass results in half the acceleration. Let's say we change that, and instead of making the cart heavier, we're going to take weight off of the cart and make it lighter. Well, if you half the amount of mass on the cart, then it's smaller, and you're pulling on it the same amount as before. So something smaller, when you apply a force to it, should go farther and faster. So we should get twice the amount of acceleration, hypothetically, if the mass is reduced by a factor of 2. So half the mass results in twice the acceleration. And again, this kind of makes sense because halving one of the things and doubling the other thing and then multiplying them together should equal the same amount that you originally had for your answer. So instead of being proportional, we would say in this case that m and a are inversely proportional. You may know in math that the word inverse means the opposite of something, so we are seeing a pattern that is the opposite of proportional, where m and a are both changing the same amount, but in different ways. M is decreasing by a factor of 2, and A is increasing by a factor of 2. So they're doing the same thing, but opposite. That's inversely proportional. So if you plot M and A data together from your lab today, and you see a pattern like this, that actually is an inverse proportional relationship. And if you look at what happens as mass increases, as the cart gets heavier and heavier and heavier, the amount of acceleration it experiences drops. And then the reverse is true as well. As the cart gets lighter and lighter and lighter with less mass, you end up getting higher accelerations. So all of these three different things on the bottom here, the equation, the statement in the middle, and the graph, are all basically saying the same thing. What they're saying is F equals ma is a real valid equation. It's confirmed to be true if m and a show a inverse proportionality. But F equals ma will be debunked in today's lab if m and a do not show inverse proportionality. So this is the slide you can refer back to when you're trying to figure out if F equals ma is legit or not. So that should get you ready for today's lab. I wish you luck in your studies. Oh wait, there's one more thing. Unfortunately, one of the variables in today's lab, either F or M or A, is actually going to be kind of tricky to measure and to consistently get the same amount that you're looking for all the time. So which of the three is going to be the challenging one? Well, let's go through the list. Selecting the amount of mass that you're using in your experiment is going to be pretty easy, and that's because you can simply add or remove known values of mass to the cart. All the masses we use in our class have little labels on the side, so you'll know exactly how much mass you're using. And for the cart, we have a scale that we can measure the mass on, so that one's easy. What about acceleration? Well, measuring the acceleration is going to be easy-ish, because if you're doing this lab in person, then you're probably going to be using a motion sensor, and the motion sensor can create a velocity time graph of the motion of the cart as it accelerates. And if you remember from a previous unit in the year, the acceleration of something is equal to the slope of the VT graph of that motion. So you'll be able to run through that and press a couple buttons and figure out what the acceleration of the cart was after it moved. So that's not super easy, but it's definitely manageable. So it must be force. What is it about force that's going to be really hard to be consistent about? Well, how are you going to know if you're pulling on a string that you're always pulling with a consistent amount of force? And the answer, of course, is that you're not going to know exactly how much force you're pulling with. If I told you to pull with 50 newtons of force, would you be able to A, know how much that force is, and B, pull exactly that hard every single time? You wouldn't be able to, unless you're really skilled or a robot, which I don't think most of you are. Yet. So the solution here is, instead of you pulling on the rope, we're going to let gravity supply the force, because gravity is something that does pull consistently the same all the time. And even if we move left to right in the classroom, or the wind blows, or someone coughs, or someone moves somewhere else and then comes back, gravity will always be operating at exactly the same strength in our classroom all the time. So how are we supposed to use gravity to pull on this rope to get the cart moving? Well, we're going to sort of change the direction of the force. Instead of having a hand pulling on a string, pulling the cart, we're going to attach our cart to a pulley system, and we'll have a hanging mass over the edge of your desk. So that hanging mass is going to have a gravitational pull. There's going to be a force of gravity pulling it down, and that's going to supply the force in this case. Now, how much force are we going to get? Well, the force of an object that's being pulled down due to gravity, aka weight is equal to the mass of the thing that's being affected by gravity multiplied by g, which is 9.81 meters per second squared. So we can actually figure out exactly how much force is going to be applied. We don't need to pull with our hand and wonder if it's 50 newtons. We can calculate exactly how much force is going to be applied to our system based on knowing how much hanging mass there is, and then multiplying by 9.81, and that'll be the amount of force applied to our entire system. Now, that's important to note, is that pulling force is not just going to affect the hanging mass, and it's not just going to affect the cart on the top, it's going to affect the whole system, because both of those systems of masses will move all together as one. So that makes F equals ma, that equation I've got in the brown area there, that makes it kind of inaccurate to just say F equals ma. You'll notice I've got two m's in the diagram because there's a big M for the cart, which is going to weigh a lot, and there's a little lowercase m for the hanging mass, which is going to be pretty small. So this would actually be a more accurate way to describe our system now. Instead of saying F equals ma, I'm saying F equals big M plus little m times A. So I've replaced the single m with the two m's because we have a system of two objects here, and we need to add their masses together because we have two things being moved by that gravitational force, so we have to consider both of them. So this would be the equation that could calculate how much force is going to be affecting these objects, but we actually already have on the side here on the right an equation that will tell us how much force is being applied. So something that might be more useful perhaps is a version of this equation that solves for A. We want to be able to predict how much acceleration this system will experience. So how would we solve for A in this kind of updated formula? Well, to get A by itself, we would want to divide both sides of this equation by big M plus little m, and dividing by big M plus little m on both sides would make it look like this. The force being applied to the system of masses divided by the system of masses equals the acceleration of the entire system. Are you intimidated yet? Maybe you should be a little bit, but now that you have the basic idea of this lab, once you dive into it, you should be able to recognize what you're supposed to do each step of the way. And I think you'll start to see, is F equals ma a real thing by the end of your lab, to the point where you'll be really confident on your answer of yes or no. And of course, having an excellent explanation of why it's yes or no will be just as important. So I wish you luck in collecting your data and forming your conclusions, and I'll see you in the next video.